tady zdroj určitě.
Yep.
Ne, tady už je vegáčka. Tak možná to dneska nefunguje. Máme vegáčku nastavený zdroj. No. A tady to nevidíš. Jo?
Co tentokrát? Nechci zapnout ten počítač velký.
Máš tam nějaké srdce?
No mám to na tom,
To je místnost toto.
Zkus tímhle.
No,
Kde máš FN tohle?
No.
Jo.
My tady vůbec nevidíme.
To nezobrazí na počítači.
Tak nemá listu.
Ale...
No, musí tam mít duplikaci. Display ven.
No, neukazuje mi to vůbec.
Můžeme používat když tak tady ten velký počítač, abychom si na něj dávali.
Můžete, jo. Máte flešku, tak to není problém.
Jo.
Jako evidentně to jede, jo. Musí z něho vyloudit výstup.
Bychom měli začínat.
No dobré, tak já to zkusím. To je... To je... Download this. Dev. Máš? Flašku? Super.
Máš počítač.
Nič. Zase nejde ani flačka. Tak já si zkusím
Systém problém.
Feveru.
Není to teda online, když to máš na Google?
Možná se přes A, už to kliknu. To je... Ty vole, to nič nefunguje dneska. Můžeme paste. Já se přihlásím asi na...
Tak to zkus tady v tom počítači.
Jo, to platí pro všechny učebny na loga nesahat.
Jo.
Tak já pustím tady tohle.
Ještě počkej, ještě hledáte heslo.
Aha, dobrá. Já se hodím zpátky teda.
To zase nejde Ctrl-V.
to chvilku trvá.
Můžeme začít?
Hello everyone, sorry for the delay and please welcome our next speaker, Kirill Pokorny with his lecture about TLS and DTLS in Linux kernel.
So, hello everyone. Welcome to my presentation about AFK TLS. We will discuss basically address family kernel transport layer security, and we will discuss basically a Linux kernel that implements part of TLS and DTLS protocols right inside the kernel. So, before we start, let's discuss about TLS and DTLS in a nutshell. So, TLS stands for Transport Layer Security. The DTLS means Datagram Transport Layer Security. You are probably familiar with the term SSL, that is historical naming. Now the proper way to call this protocol is TLS. We have currently version 1.2. There's a draft that describes version 1.3, and it introduces a lot of cool stuff such as zero round trip time. So you basically sending data with the handshake. You probably know libraries such as GNU-TLS and OpenSSL. These are open source implementations of these protocols. You are probably familiar with other libraries such as LibreSSL, but most of them were basically forked from OpenSSL due to some vulnerabilities. If we look at TLS and DTLS protocols, basically we can see that we have a control layer and the record layer, and basically the control layer is used to control TLS and DTLS protocol. So you can see messages like, hey, I want to establish connections, so I want to establish keys, or hey, I want to do rekeying when there's some problem with the session and we might be compromised. And then there's a record layer. Basically, the record layer is used for transferring your data. So if you transfer your data, it's in the record layer. The main difference between TLS and DTLS is that TLS requires the underlying protocol to be reliable. That means that you have to use protocols such as TCP. On the other hand, DTLS protocol does not have such requirements, so you can use it on top of UDP. On the implementation level, that means also that if you are implementing DTLS, you have to deal with things such additional information, so you don't receive some records twice, and you are basically dealing with reply attacks. If you are using web, you probably are familiar with TLS. Basically, HTTP protocol is used quite widely with TLS, so called HTTPS. The S stands for secured. TLS is also used for email, and probably not that known projects are high availability proxy. That is basically a load balancer on top of TLS. And also we have SSL-based VPNs. The SSL here is a term that is quite tightly bound to this expression, but it can be also TLS-based VPN. Such VPNs are OpenConnect, that is open source implementation. It's open source implementation, but there is also AnyConnect, that is implementation by Cisco. And basically OpenConnect is alternative to AnyConnect, and it's also compatible with AnyConnect. If we look at very basic scenario, we have a client that communicates with some device that is located on local area network, and we are communicating through WAN. So we want to take care that our communication is encrypted and no one sees what's going on and what we are basically sending. What client needs to do to basically send data? There needs to be established connection, but once we are done with the connection establishment, we basically do encryption, and we add some additional information such as header and tag to our message. So it's TLS specific. Then when we are done with encryption and the encapsulation, we basically write the record to the kernel, and kernel does all the things for us. It basically sends the record on the wire or any other media you use for transferring your records. And once your record is on the server listens on some particular port, and once your record is ready, you basically, or OpenConnect server basically issues read or receive operation, and it decrypts our record. So basically there's reverse operation to the client. Once we decrypt, we check integrity, and once we are done with it, we have raw data that was transferred, and once we have raw data, OpenConnect server basically issues write, and our record is routed through the kernel to desired device on local area network. If we look at this scenario, we can see that on the server we are basically reading from the kernel and writing, and we are reading just to do decryption in user space. If we try to identify this thing and basically move the decryption to the kernel, we basically do an optimization, and if we take a look at it, we basically saved 2 context switches. So we are no longer required to do read-write and to user space. And what we achieved, we also achieved that data that were transferred are no longer copied from kernel space to user space for the decryption, and from user space to kernel space for sending. And basically, this was the idea behind AFK-TLS. So address family kernel transport layer security. It's a module. It's a Linux kernel module that sits right inside your kernel, and it basically introduces a new socket type, AFK-TLS. It implements part of TLS and DTLS protocols. There's only implemented the record layer, so if you want to use AFK-TLS, you have to do handshake in a user space with your libraries such as OpenSSL or GNU-TLS, and once you establish the connection, you basically ask these libraries for key material, and you instantiate AFK-TLS, and then you pass all this key material to the kernel, and you can do read-write operation on a socket just like raw socket, and you are basically accessing raw data from the socket. Currently there's implemented only ASJCM cipher, but AFK-TLS can be extended with other ciphers as well. Very nice candidate is Chachapoli that is used on mobile devices. AFK-TLS supports all socket operations, so you can do socket to instantiate AFK-TLS. You can do bind, send, receive, or write and read. You can also do some advanced stuff like send file or splice. And the only socket operation that is not supported is connect. Basically, when I was designing API, it didn't make much sense to implement connect. There was no semantics for it. So if we look at the optimizations, we wanted to save context switches. Basically, this is not possible now with Linux kernel because there's no such syscall that would do something like, hey, this is my socket, and read everything from this socket and write to another socket. There are syscalls such as sendFile and splice. Basically, sendFile is used for sending files, and it's implemented on top of splice syscall. And splice system call is designed to basically do things like, okay, I have a socket or file descriptor, and I need a structure that basically points to the kernel space and points to memory that is allocated in user space. So I'm no longer required to copy from user space to kernel space. Such a structure is called pipe, and you can use AFK-TLS mostly with sendFile and splice, so you reduce copies, and this optimization was quite successful. We are no longer required to copy data from kernel space to user space only for decryption or encryption. When we were implementing AFK-TLS, there were issues such as issue with padding. When you do optimization, you have to take care about a lot of things. Such thing is padding. If we look at TLS record, we can see that there are basically 5 bytes, and everything that follows is shifted. So we are not aligned, and we are accessing memory that is not aligned. The same applies for DTLS record. As you can see, there's a sequence number that is carried to construct a sliding window. Here are some results, and basically, as you can see, the send file using AFK-TLS is the fastest way how to transfer data over TLS or DTLS. It's faster by 5 to 10%, like 7% in average. Here is user send. That means it's sending data through UTLS or OpenSSL send. So you are doing basically encryption and decryption in user space. And the last bar represents a map when you map whole file into memory, and basically you do send using user space library. So you do encryption and decryption in user space. So AFK-TLS has various usages. Basically, it was designed for Open Connect and high availability proxy, but as it showed, it's not possible to use it because there's a lack of tune device support for splice system call. But AFK-TLS could be used for example, with KCM, that is a kernel multiplexer where you have a socket and you can do multiplexing with various threads in the user space. You can also, with AFK-TLS, you can also access raw data right in the kernel. This gives you power to use Berkeley socket filtering or Linux socket filtering. You can also use BCC. That's a nice tool where you basically say, hey, every time there's called this function in the kernel, I want to run my code. So BCC allows you. And probably the most useful thing for AFK-TLS is CPU offloading, where you basically have a specialized hardware which does encryption and decryption for you. And this allows you to offload CPU, so you can do something else on CPU. Basically, two companies contacted me, and both of them were using AFK-TLS for CPU offloading.
How much does the Linux kernel crypto API help, if at all, with these kind of things?
Sorry?
The Linux crypto kernel API, does it help at all with these things? Are there ciphers you can use? Basically, it supports crypto hardware already. What kind of thoughts have you in that regard?
So the question was if Linux crypto helps in this way. So with AFK-TLS, we are using Linux crypto. It was needed to patch it because there were some issues with implementation of ASJCM. Basically, Facebook patched it. And TLS in the kernel is not novel. There were implementation in Solaris. Solaris implemented whole TLS protocol into the kernel, and it acted like a proxy. So you had one port to another, and it was basically forwarded. Netflix experimented with something similar to AFK-TLS. They adopted BSD kernel. This implementation is not open source. They published few articles, and they were basically adapting OpenSSL. We experimented with AFK-TLS at Red Hat and also cooperated with Facebook, who sent a few patches. You can find AFK-TLS on the GitHub, and that's it. So, any questions? Yeah?
Do you have a merge target timeline
Merged?
for upstream?
Not. So the question was if we merge this to the upstream. Not yet. There are still open issues that we need to deal with, and basically it could be merged someday, hopefully.
Do you know where the performance increase comes from? Perhaps the 5% to 10% better performance you're doing in use post. What are you doing better?
Sorry?
Can you explain where the performance improvement comes from? Why is performance better by doing it in use post?
So if I understood it correctly, what was basically the key in the optimization? So the key in the optimization was that we reduce number of copies, so we are no longer required to copy from kernel space to user space and vice versa. Yeah.
So is it going to be used in HA proxy?
HA proxy uses Tune device to communicate, and Tune device does not have support for splice, so it's not possible to basically use it with HA proxy right now, but once the splice support will be in Tune device, it will be used easily.
How do you deal with a synchronous TLS alert, which is happening on the wire?
Sorry?
How do you handle a synchronous TLS alert that happens on the wire in the data stream?
So the question was like how we do synchronous
TLS alerts
on loads.
on the wire. So if you have your TLS connection already set up and you get a renegotiation event, how do you send that to user space?
So basically, when you use AFK-TLS, any error, we basically check only if it is data, and if it is not data record, we immediately return error to user space, and we notify, hey, this is not data, and all the key material has to be passed again to user space libraries, and basically user space libraries have to deal with some special cases there.
So you can't use libraries anymore for dealing with TLS. You need to implement that. You can't use like a normal socket like we used to do that in Linux, where you pipe or give that file descriptor ID to some other.
Basically, we have two file descriptors. One is the file descriptor that is used for encrypted communication.
Yeah.
And then there's another one, AFK-TLS, where you access decrypted or decrypted data. So you are basically playing like ping pong when you want to use the encrypted socket. You have to pass all the key material from kernel space back to user space because there's also
Okay,
state.
then how do you deal with asynchronous errors on the TCP layer while keeping intact the POSIX rule that you always get on a new file descriptor the lowest file descriptor number?
The question was how do we deal with errors on TCP layer? Basically, any error that is on during communication, we notify user space, and user space has to deal with it.
But somehow you lose those file descriptors.
Somehow
You have to close those file descriptors, or do you keep them dangling?
you keep that open, and basically basic